Chapter 6, Newton's Laws of Motion. There are three laws that we are going to cover, the first, second, and third law. We have already covered that a force is a push or pull, or any action that is able to change motion. So Newton talked about how this motion occurs. And his first law says that objects continue the motion they already have unless they are acted on by a net force. If the net force is zero, the object will stay at rest. So it's not going to move. Remember, we talked about forces being identified with vectors and finding the net force by looking at the vectors. If an object is acted upon by an unbalanced force, its motion will change. So these are two key points here. So we say Newton's first law is often written in terms of the net force. An object at rest will stay at rest, and an object in motion will continue in motion at constant velocity unless there is a net force. Newton's first law is also called the law of inertia. Inertia is the resistance to move. So we have this golf ball that's sitting here. It has the normal force pushing upwards, the weight of the golf ball being pulled down by gravity, friction from contact with the ground, but then you have the force of the club, which is much larger. So your overall net force in this case, these cancel out because they're the same, but your force of the club overcomes the friction, therefore the motion of the ball is to the right. When we look at Newton's first law, a lot of things are explained by watching the car driving into the brick wall. What happens to the driver? As he flips over, he continues to move because the car was stopped. So an object in motion remains in motion. An object at rest stays at rest unless acted upon by an outside force. So the car being in motion continues, hits the brick wall, it stops, but the body continues in motion. Now this is similar to when you ride a roller coaster, and if you're dropped down from a height, you always feel like your stomach's up in your throat. Well, it's kind of true because the ride drops first, then you're belted in, and then that belt forces your body to move with the car, but with inside your body your organs are distended. So that then means that the organs are the last thing to kind of move, so that they get pushed up inside your body feeling like they're going to come up, but they can't. But that's how you get the feeling in your belly of going over hills and being dropped on roller coasters. The law of inertia, like I said, the property of an object that resists changes in motion. Objects with more mass have more inertia, and they are more resistant to changing their motion. So comparing a bowling ball to a golf ball, which ball has more inertia? The bowling ball, because it has more mass. And here is just a video clip on Newton's first law. which leads us then into Newton's second law. Newton's first law tells us that motion cannot change without a net force. So if you have a ball sitting there, it's not going to move unless there's an outside force on it. Something has to come in contact with it, whether it's gravity or a hand to push it or a foot to kick it. According to Newton's second law, the amount of acceleration depends on both the force and the mass. So here you take that ball, and we have to take in consideration the force that is maybe kicking the ball or the ball itself and the mass that it is. Is it a small ball or a big ball? The Newton is the amount of force needed to accelerate a 1 kilogram object by 1 meter per second. So basically, it's the amount of force to move the object. So we measured this in the last lab of a Newton, what it is to pick up an apple or a 500-gram bottle of water. There are three main ideas related to Newton's second law. Acceleration is a result of unbalanced forces. A larger force makes a proportionally larger acceleration. Acceleration is inversely proportional to mass. Okay. So let's look at these. So the second law says that acceleration is proportional to force. So if the force is increased or decreased, acceleration will be increased or decreased by the same factor. So here you have 1 Newton pushing on the mass of 1 kilogram. So your acceleration is 1 meter per second squared. Now double that force to 2 newtons, keep your mass the same, but you increase the acceleration by the same amount that you increase the force. So now we're 2 meters per second squared. Decrease the force by half with the mass remaining the same, and you decrease the acceleration the same amount you decrease the force. So it's proportional. Whatever happens to one will happen to the other. When you look at another factor, is that the acceleration is always in the same direction as the net force. So you have a positive force pushing in this direction, you're going to have positive acceleration in the same direction. Same thing if you have a negative force pushing it backwards. And think about a sideways force. I always think about a car getting T-boned, so it comes in and hits the side of the car. Well, it's originally driving this direction, but because the force is coming in this direction, it's going to have a sideways acceleration due to that sideways force. So the direction will change of the car. Instead of continuing in the straight path, it will curve. The greater the mass, the smaller the acceleration for a given force. This means acceleration is inversely proportional to mass. So here we have our car from our lab, and there's no riders in this car. It's empty. So the force that acts on the mass to cause the acceleration is here. So this is the force. This is showing you the acceleration. It's a pretty good amount of acceleration compared to the same force acting on a car, but now we have 2 riders. So we've increased the mass. Look what happens to our acceleration. It decreased. So if you increase mass, your acceleration decreases. So the second law is F equals ma. So if mass goes up, acceleration goes down. Now if mass goes down, acceleration will go up because they are inversely proportional. So here is the formula that you can use to find force or the acceleration or the mass of an object due to Newton's second law. So the stronger the force on an object, the greater its acceleration. So force is directly proportional to acceleration. So if twice the force is applied to the acceleration is twice as great. So here you can use this cart, for example. You can use a shopping cart. Anything that you have, if you increase the force, your acceleration, you're going to increase the acceleration. Decrease the force, it's going to decrease the acceleration. Put more mass in it, and it is inversely related. So you increase the mass from 1 box to 6 boxes, keeping the force the same, your acceleration decreases. Okay. So applying the second law. So looking at this, the net force is what causes the acceleration. There is no acceleration if the net force is 0. Okay. If there is acceleration, then there must be a net force of some sort acting upon this object. The force unit in newtons is based on kilograms, meters, and seconds. So here it shows you the variety of ways to find the different variables. Again, you can go back and relate this to our equation of force equals mass times acceleration. So you cover up the F, and it gives you the force, which is mass times acceleration. Solve for acceleration, and it's force divided by mass. Looking for mass, it's force divided by acceleration. Our handy-dandy triangle. So here is another short video clip to talk about second law. Okay, so that sums up Newton's second law. Newton's third law is action-reaction. So this applies when a force is placed on any object, such as a basketball. Your hand exerts a force on the ball, that would be the action. The ball exerts an equal and opposite force on your hand, reaction. So in any sort of situation, there's multiple action reactions going on. So Newton's third law, every action force creates a reaction force that is equal in strength and opposite in direction. There can never be a single force alone without its action-reaction partner. And we talked about forces. Forces always occur in pairs. You always usually have a push and a pull. So the action of the ball or the reaction of the hands, or you could have the action of the hand and the reaction of the ball. So it doesn't really matter which one's called action, which one's labeled reaction. The forces do not cancel because we can only cancel forces acting on the same object. So we have two different objects here, the hand and the ball. So they will not cancel, so you end up with a motion of the object. When sorting out action and reaction forces, it is helpful to examine or draw diagrams using vectors. Okay, so the action force is on the ground. So you're pushing down on the ground, but as you push down on the ground, the reaction force is the ground pushing on you. So the reaction force is on the foot. So the ground is pushing back on your foot. And here is another short video that will kind of explain this. Any sort of movement that you have, writing on your paper, you're pushing the pencil down on the paper, your pencil's pushing on the paper, paper's pushing back on your pencil, paper's pushing on the table, table's pushing back on your paper. So there's all multiple chain reaction of action reactions going on. Vectors are fancy term for arrows. So you think about all of Newton's laws are happening all around you, causing everything to happen. They're very evident when people don't understand how Newton's laws work when you watch America's Funniest Home Videos. Watch that and you can see the action reactions and objects that stay in motion or stay at rest.